Right, we're going to start with section 10.7 today. This is the last section in chapter 10. And in this section, we are going to talk about complex numbers. Now, basically, what we will be doing in this section is we will look at a new set of numbers, which includes the set of real numbers, and it also includes numbers that are even roots that have negative numbers in them, like something of this form, where you have a negative number inside an even root, like negative b inside of a square root. Now, if you remember, in the first half of this chapter, we said that these were not real numbers and that you could not simplify them. But in the complex number sets, you can simplify numbers of the form square root of negative b, and that is what we are going to talk, is to see how to simplify these. And again, here b itself will be a number greater than 0. So to understand how to simplify these numbers of this form, let's go ahead and look at the equation x squared plus 1 equals 0. Okay, now if I try to solve this equation, I'll go ahead and move my 1 over to the other side, and you end up with x squared equals negative 1. Now, about here, go ahead and take the square root on both sides. I will end up with the square root of negative 1. And of course, in real numbers, you cannot solve square roots of negative 1. So what we do here is we introduce a new number, which is what we call as the number I. And what exactly does I remember? Basically, I is defined so that I square will equal negative 1. Okay, so we have this new number that we're introducing, and this number is defined as I square equals 1, which means that basically that the square of I is negative 1. So of course that means that the square root of I square, which would be just I, would have to be square root of negative 1. Okay, so if I square is negative 1, if you take square roots on both sides, you will end up with I equals the square root of negative 1. And we use this idea to help solve any numbers which are of the form square root of negative b. Okay, so let's go ahead and see how we can use the number I to help us solve square roots of this form. All right, so let's say we have square root of negative b. Go ahead and look at that first. So we are saying for any positive real number b, if you have the square root of negative b, you basically end up with I times square root of b. And why does that happen? That's because we are saying if I is square root of negative 1, the square root of negative 1 will become I, and once you take that negative sign outside, take that negative sign in terms of I, all you are left with is just the square root of b. Okay, so this is the idea behind how to use number I to work with radicals of this form. So let's go ahead and look at this example here. Now we want to write this number as a product of a real number and the number I. So we will go ahead and write this number as negative 1 times 225. Okay, so we're basically just taking that negative and putting it as negative 1 and getting the 225 as a positive number. So you're just basically rewriting it as a product of negative 1 and 225. Now, you can go ahead and break this up as square root of negative 1 and square root of 225. Okay, so we're just splitting it up into two radicals, and square root of -1 is the number I, and then you can take square root of 225. Square root of 225 is of course 15, so this becomes 15, and then you're left with the number I. And you can see how earlier we could not have solved square root of -225, but now that we have the number I, you can go ahead and solve this, and your answer will be 15I. Let's take a look at another example. Right, so let's look at negative square root of -196. So again, we will go ahead and write this as the negative on the outside. For -196, again, we can go ahead and write it as -1 times 196. Again, that negative from the outside. Now square root of -1 will become I, and you're left with just square root of 196, and square root of 196 is 14, so you have the negative on the outside. You write 14 for square root of 196, and then you write your number I. Now again, you will notice even in the last example we put the solution as 15I, and in this one we are writing the solution as -14I. It's just a general practice to write the I after the constant term, just like you would write 14x. In the same way, we just treat I sort of like if it were a variable, and you always put it after the integer term. Let's look at one more example just to be sure that we know how to work with the number I. So we have a square root of -96. So again, we can go ahead and write this as -1 times 96, and -1 again becomes I, square root of 96. Now 96 is not a perfect square, so it will not completely come out of the radical, so you will have to simplify this number. And let's see how you can write 6 as 6 times 16. Okay, and again, why do we use 16? Because 16 is a perfect square which can come outside of the radical sign, and 6, since it cannot be simplified, that will continue to stay inside the radical. So again, square root of 16 will come outside as 4. You have the number I, and then square root of 6, since we cannot simplify that any further, will continue to stay inside the radical. Now in this example, you will notice that your whole number went in the front, and the radical term stays after the letter I. So again, that's just a formal way of writing this number. You always put the constant term before I, and then if you have a radical part, that goes after the number I. All right, let's talk about another property of the number I here. Now let's say you have something of this form. Okay. Now when you're trying to find the product of numbers like square root of -3 and square root of -7, you cannot apply the product rule for radicals, because again, the product rule only works if you are talking about non-negative radicands. And here, of course, you can see that your radicands are both negative numbers, so you cannot apply the product rule that we saw earlier in this chapter. But you can try and use the same idea of the converting from the negative radicand to a positive radicand by using the number I. And by using these number I's, you can actually go ahead and do your multiplication and division. So let's see how that will work for us. So we're trying to multiply square root of -3 into square root of -7. So the first thing you will do is write square root of -3 as I times square root of 3, and write square root of -7 as I times square root of 7. So just bring the negative sign outside using the number I, and then you're left with I times positive square root of 3 and I times positive square root of 7. And let's see how that will break down for us. So of course you'll multiply the I times I, which will give you I square. And now that these are both positive radicands, it's positive 3 and positive 7, now you can apply the product rule for radicands and multiply the 3 and the 7. Again, remember, the product rule said that they have to have the same index number if you have to multiply the radicands inside. And of course, your radicands have to be positive numbers. So now that we multiply 3 and 7, you end up with I squared times square root of 21. And we talked about this earlier where we said I square is equal to negative 1. So that's where this negative 1 comes from. And you end up with negative 1 times square root of 21, which will of course give you negative square root of 21. So this is the idea you're going to try and apply anytime you are multiplying two even roots that have negative radicands inside. So let's look at a couple examples here on how to multiply or divide numbers of this form. So let's say we have negative square root of negative 4, and we're trying to multiply that with square root of negative 25. So just like we saw in that example, we'll go ahead and write negative 4 as I times square root of 4, because again, remember, the negative 1 as a square root will come outside as I, and square root of negative 25 will be I times square root of 25. Now, of course, we know that both 4 and 25 are perfect squares, so you can write square root of 4 as 2 and the I. On the other side, square root of 25 is 5, and don't forget your I again. So you will end up with 2 times 5, which is 10, I times I, which is I square. And of course, we know I square equals negative 1. So you'll end up with 10 times negative 1, and your answer will be negative 10. Okay? Just as simple as that. Let's take a look at another example. And here also we're trying to multiply. So this time you have square root of negative 10 times square root of 2. And of course, this is a positive radicand here, so you don't have to worry about this guy. But this term is square root of negative 10. So again, you will start by writing this as I times square root of 10. And then this stays the same, square root of 2. Okay, now that these are both positive radicands, you can apply your product rule. And you will end up with 10 times 2, which will of course give you 20. Now again, same thing happens here. We know that 20 is not a perfect square, but we can try and simplify this. And you can write 20 as the product of 4 times 5, because again 4 is a perfect square, so 4 can come outside of the radical as 2. You're left with I. And since you couldn't simplify 5 anymore, that ends up staying inside the radical, and you end up with 2I square root of 5 as your product when you multiply these two numbers here. Okay, in the same way, we want to take a look at examples that involve division. So let's see how we would work with a problem like this. Right, so let's say we have square root of negative 40 over square root of negative 10. Just like we did with the multiplication problems, go ahead and rewrite each one of these as a product of I and a positive radicand. So this will give you I times square root of 40 for your numerator. For the denominator, same thing, I times square root of 10. Okay. Now, just like we did with the quotient rule, you can now go ahead and apply the quotient rule also, because both your radicands are now positive numbers. Now, just like we would do with any other division problem, since you have I over I, both the i's will cancel each other out, and you will be left with 40 over 10 inside the same radical using the quotient rule. And 40 divided by 10 will of course give you square root of 4, and square root of 4 is 2. So you can see how this problem actually works out, and you end up with a nice and clean answer as the value of number 2. Okay, we'll try and apply this to one more example. In this one, you have square root of negative 75 divided by square root of 3. So again, you'll see only one of the radicands is negative, so go ahead and make that a positive radicand. So bring the I on the outside, and you are left with square root of 75 over square root of 3. Now again, since both our radicands are positive, now we can go ahead and combine the two together, so you will end up with 75 over 3. Now again, since we did not have an I in the denominator, you cannot cancel this I out, so that I will just keep carrying over in your answer. Now when you divide 75 by 3, you will end up with 25 as your answer. Okay, and of course we know square root of 25 is 5, so you end up with 5i as your answer to this problem. So you'll see in the first example we got rid of the I and you ended up with only 2 as your answer, but in the second one, since the I was still in our problem, you end up with the I in your final answer as well. Alright, now we are ready to talk about complex numbers and talk about what the imaginary complex numbers mean. Okay, so let's go ahead and see what a complex number is. Now, if you have a and b as your real numbers and you write it in the form of a plus bi, again where we're using the number I there, this form is what we call as a complex number. Now, just to identify this, let's go ahead and see what the number breaks down into. Now, if you look at the number a, this is what we call in part, from your complex number here, your a is called the real number part or the real part, and b is called the imaginary part. Okay, and the idea is when b equals 0, so that means when b equals 0, a plus bi is a real number. So if b equals 0, then we know that 0 times I will be 0, and that imaginary part will disappear, and you will be left with just the a part, and we know a is a real number. So that's why we say when you have a complex number of the form a plus bi and b is 0, then this number will become a real number. And that tells you that real numbers are actually a subset of the complex numbers. Okay? And of course, if you don't have b equal to 0, if b does not equal 0, then that number will be called an imaginary number. Okay, so when b does not equal 0, these numbers are called imaginary numbers. Now, some textbooks will give you a definition where they say that the number bi is the imaginary number. Okay, since that is the imaginary part. Okay, so some books like to say that if a equals 0, which means this part disappears, and you're left with bi, they like to call that as the imaginary number also. So, for our textbook purposes, we are just going to say that when b does not equal 0, then that complex number is called an imaginary number. Okay, now let's go ahead and talk about the relationships between the many different sets of numbers that we have used. So let's go ahead and see how this breaks down. Now, complex numbers, we know, are broken down into imaginary numbers and real numbers. When b equals 0, it becomes a real number. Okay, and when b does not equal 0, that's when we call it an imaginary number. Now, real numbers will further break down into rational numbers and irrational numbers. Again, remember that rational numbers are of the form a over b, and irrational numbers would be something like square root of 5, square root of 7, those sort of things. And rational numbers, you can further break it down into integers and non-integers. Okay, so you can kind of see how the whole relationship works out here. So you can see complex number is the big set, and then all of these other sets are subsets of the complex number set. Now, imaginary numbers, even though we use the word imaginary, are very useful, especially in applications like electricity. So I suppose you're not going to use these in everyday situations, but if you do happen to work in that field, you will know what we're talking about.